Let's start our lecture number 21, and we are going to work on the example on the analysis of the statically indeterminate frame. Okay, and then we should go to the task. Hello. โอเคจ้ะครับส่งเมลให้จันนิดนึงก็ดีหรือส่งทางไลน์ก็ได้ครับจ้ะครับสวัสดีครับโอเค Okay, let's start our lecture and following the paper อาจารย์ provide you we come to this example. It is the rigid frame and this rigid frame has pin support and have the rigid connection, and we're going to select the B sub X as the redundant. So please read the problem statement clearly. Which one gonna be the redundant? Okay, I cannot allow everybody to select the redundant, so that's going to be a very big problem. You're going to get the same redundant. And then under the application of this one, you got to read this one. The factorial stiffness or factorial rigidity of the frame. Sometimes Ajahn said it's going to be 2EI. Sometimes it has only EI. Under the force of 16 kilonewton per meter, we're going to determine the reaction, draw the shear force diagram, and draw the bending moment diagram. And then we're going to use the consistent deformation method. And then we got to consider the frame following this given. So basis upon this one, we have DOI equal to what? This is going to be 1 reaction single pin, and this is going to be 2, and this is going to be 3, and this is going to be 4 reaction minus 3 free body, 3 equation for 1 free body diagram. So DI gonna be 1. And that basis upon the given information over here, B sub X gonna be redundant. So by using the principle of superposition, we separate the the frame into 2 frames. Okay, we separate the frame into 2 frames. One gonna be primary frames, and the other one gonna be the frame that's subjected to the redundant force. So the first one that's gonna be to 5 meter. Let me put it into 25 millimeter, and this is 4 meter. I should put it to be 20 millimeter. Since you said B sub X is going to be our redundant force, so at the point B of the primary frame, you got to change the pin into the roller. Change the pin into the roller and free from B sub X. And then at the point A, the structure still have the pin support as usual. Primary frame gonna subjected to the given external loading. So it's going to subjected to 16 kilonewton per meter, and then you're going to combine it with the same frame, but it's gonna subjected to the redundant force. So this one 20 millimeter still be the same roller and the pin. And over here, the structure subjected to redundant force. And then you got to draw the elastic curve of this two frame. Under the application of the force, this beam gonna be formed like the simple beam, right? The beam gonna deform like simple beam. And then over here, it's got to keep the 90-degree angle. And then under application of the force, over here has only vertical direction. This portion has no moment, as m equal to 0. So this one will be the straight line. And then the deformation of point B will move to this one. And we will call the horizontal displacement over here delta B sub X or sub H, whatsoever you like. Let's put it in the sub H. Then the second beam, when it's subjected to the force B sub X, I think it should have this kind of horizontal displacement. So basis upon this one should be curved. Why? Why this one should be curved, Ajahn? Since if you cut it over here, the force B sub X, will produce the moment over here. Okay, so this one should be curved like this one. And then it must keep the 90-degree angle, and this beam should have this kind of elastic curve. Okay, okay. So basis upon the elastic curve, basis on the elastic curve. Okay, we have the compatibility condition at point B. Okay, compatibility at point B, what? This is gonna be 0 equal to this is gonna be delta sub BH in this direction, and this is gonna be delta sub BH time in the negative. And then since B sub X is unknown, okay, we assume it to be 1.0, and then you will get this one gonna be the displacement at point B due to 1 unit load applied at point B and time B sub X. Now you have this equation in the form of this one. So 0 equal to delta sub B H minus F sub BB and then B sub X. And this is going to be your compatibility condition at point B. This is going to be, or you may rewrite it, it's going to be B sub X equal to delta sub BH divided by F sub BB. Okay. And then following the problem over here, it said, given that the horizontal displacement equation due to the redundant force B sub X is going to be 48 B sub X divided by EI. So the problem provides you what? The problem provides you with this information. Okay, and you will know that basis upon this one, F sub BB, F sub BB gonna be 48 over EI. And in this direction, this is not correct, but it's just know about it. Okay, you assume this one, but even though they provide you in opposite direction, don't worry. Okay, you just follow your compatibility condition. You know this is going to be the correct value. Okay, อาจารย์ provide you, but the direction just mistake. By doing this one, it mean this is positive. Okay, in this one is gonna be negative. You already provide negative over here. Okay, so don't worry. Now, the problem going to be the same as what? The same as chapter 7. You're going to determine the deflection equation for the primary frame. That means you got to determine delta sub BH. Okay. Any question based upon this first portion? You understand that's right? So when we put this one gonna be first step. This is going to be your second step. And then the third step, you're going to determine delta sub BH. Okay, by using the method of virtual or virtual method, depend on you gonna call it. And then if you use method of virtual work, please write the virtual work equation, because it is important to say about 1.0 unit load. Okay, if you want write it, where is the 1.0 virtual unit load? Okay, so you got to write the virtual work equation. And if you prefer, you may put it in a more complicated, such as external virtual work is gonna be equal to internal virtual work. So basis upon this one again, 1.0 unit load come what? The virtual force gonna time the real displacement delta sub BH. Okay, that mean we're gonna have another frame. Okay, and that frame gonna have what? Gonna have the same support, and it's gonna subjected to 1.0 virtual force, 1.0 unit load virtual force times the real displacement. We call it external virtual work. And then it's gonna be equal to, due to the continuity of the frame, we got integration. And then this 1 unit load gonna cause the internal bending moment due to virtual unit load. And then this one will have the zeta, and then we have the zeta equal to m dx over ei. Okay, that's why you got to write equation in order to explain the method. Now you come to the calculation, as you also have it. Okay, let me put this one for capital M. So the first one, let me put it 5 meter. Let me put it a bit bigger. Okay, like this one. And that's gonna be A, and this is gonna be C. And let me put over here, this one gonna be point B. Under the application of 16 kilonewton, you got to determine again the reactions. Okay, the reaction of here gonna be only B sub Y. Then over here, you should have the A sub X, and over here you have A sub Y. Okay, so summation moment equal to the force F F sub X first. F sub X equal to 0. A sub X gonna be 0. Then you do the summation about A equal to 0. What you get is going to be B sub Y. B sub Y gonna time this is gonna be 5 meter. Let me put it over here. Summation about A over here to be 0. This gonna be on this rotation 5 B sub Y equal to this force. This is gonna be 16 times 5 and 16 times 5 and then square over 2. Okay, you should cut this one and then it's gonna be 16 times 2.5. You got to get B sub Y equal to 40 kilonewton. Okay, and then the last one, summation of F sub Y equal to 0. Upward is positive. A sub Y plus 40 equal to this one, 16 times 5. 16 times 5 is what? 90. No, 80. Okay, 80. So A sub Y is gonna be 40 kilonewton. So this one 40 kilonewton. Now you got to set the coordinate for the calculation. It's up to you. For this one, let me put this one to be x1. Okay, and then let Ajahn put this one to be x2. If Ajahn said this is going to be x1, you just cut it over here. This frame subjected to this 16 kilonewton per meter, and you have the force over here of 40 kilonewton. And then you're looking for what? You're looking for capital M1. Capital M1. And you got to be very careful on this one. You got to select a small m based on the same coordinate and the same moment. So summation moment equal to 0 over here. Putting this rotation, you have capital M1, and this is going to be 16 plus 16 times x1, and the distance from here to here gonna be x1 over 2, and then you got to get equal to this one 40 x1. So capital M1 is gonna be 40 x1, and then minus 8 x1 square. Okay, you got to have this first term. Let me put it. That's gonna be capital M1. Then coming to the second portion, cut it over here. The portion subjected to the force B sub Y. And then if you put this one to be capital M2, and then as you set summation of the moment equal to 0, you will see capital M2 gonna be 0. Okay, that's why I explain over here. This portion gonna be straight line since there is no moment. Now you come to the next step. Determine the small moment M. Now you draw the frame and then put the support. This is the roller, and then this 1 unit load is what is going to be the same as this one. Let me zoom out a bit from what we have over here in this direction. Okay, cap the small m gonna be due to the virtual 1.0 unit load here. And since this is the roller, let me put this one to be B sub Y. And this is still be the pin. This is gonna be A sub X. And since no vertical load, this is upward. This gonna be downward A sub Y. And let me put the summation of X sub X equal to 0. A sub X gonna be 1.0. Okay. And then if you take the moment summation moment at A over here to be 0, take the moment. B sub Y gonna rotate in this direction. And this is 5 meter. 5 times B sub Y rotate in this direction. But the line of action of 1.0 unit load gonna time what? Gonna time this is gonna be 4. So it's gonna be 1 times 4. Our B sub Y gonna be 4 over 5. That's gonna be 0.8. Okay, 0.8. And then if you do the summation, F sub Y equal to 0, downward positive, A sub Y gonna be 0.8. Basis upon the same. Putting this one to be X1. You have the portion of the frame subjected to this is 1.0 and this is 0.8. And then this one gonna be small m. You got to put it in the same direction, small m. Okay, and then summation of the moment equal to 0 in this direction, positive. You have what? 0.8. Okay, and then this 0.8 rotate in the same direction. So small m1 gonna be minus 0.8 x1. Okay, you get me right? It rotate in the same direction. So just put this one over here. Okay, put this one over here. That's upward. This is downward. And this is going to be your M1. Now, for this one, you may cut it over here and then this portion subjected to the force of 0.8 and this is gonna be 1.0 and this is going to be x2. You do the summation moment equal to 0 in this same direction M2. Rotate in the same direction gonna be minus x2, right? This provide no moment and this one gonna provide you with the x2. That's correct. Yep, it should be k. Okay, it should be okay. And then just put this one to be 0. This one to be minus x2. Okay. And then what you get over here? You got to do the integration. So 1.0 delta sub BH gonna be only these two terms. These two terms multiply it and you get it to be 0. Okay. Okay. It will be 0. And then อาจารย์ put it in this direction, right? So the integration is gonna be integration from here to here, from 0 to 5 meter. And then you have this one 40 x1 and then minus x1 square minus x1 square. And then basis upon this one. Put this one in this direction. Okay. Oh no, this is wrong. This, sorry. I'm doing a wrong determination. Take the moment about 8. Take 5 times b sub y. Rotate in this direction. And then this one is gonna be plus. And then this is gonna be equal to 0. So b sub y is gonna be negative 4 over 8. Okay, it's rotate in this direction, So I'm sorry, this is going to be in the opposite direction. This is gonna be in opposite direction. Why? Because one gonna rotate this direction, right? So b sub y, if you put it, it's gonna be in this direction. Okay, this is going to be correct direction, but it's going to be minus 0.8. You got to change this one to be downward. If this one is downward, let me put it in a correct one. This is going to be downward. This one going to be upward. So this one going to be upward. And this is going to be in this upward direction. So the moment over here gonna be positive. Okay. So marking the direction supposed to be very careful. After you get this one, this is gonna be 0.8 x1. Now this is the x1 over EI. Okay. If Ajahn said 2EI, it's gonna be divided by 2 EI. This is only EI. And then you get this one to be, I get this one to be delta sub BH equal to 333.333 over EI. And it's positive. Okay, that means it is in this same direction as the 1.0 unit load, putting in this direction. Okay. Ajahn, if I would like to check for F sub BB, okay, if you prefer to calculate for F sub BB, you can do so for the review. Let me take you back over here. If you prefer to calculate F sub BB also, then basis upon this picture, actually, this one subjected to b sub x, and b sub x gonna be equal to 1.0, right? So this is gonna be 1.0 times f sub bb, and then it's gonna be equal to integration. We're gonna have the frame also. Okay, our frame now subjected to 1.0 force in this direction. Okay, in order to provide this kind of displacement. And then due to the 1.0 unit load, we have this one for M. Okay. And then for this one, this is B sub X, right? B sub X cos capital M. However, the B sub X is only one unit. So this one will provide M also. And this is going to be dx over EI. And let me zoom in for this one. And the pattern going to be thing like this, small m. Okay, always like this one. Ajahn, this is going to be opposite to this one. Sure. This is going to be opposite to this one. But what, Ajahn? The moment just change the direction, right? So if you prefer, you may dock it again and do the calculation. Follow the force of one unit over here. You got to get the force of this one for A sub X. If you take the moment over here, this rotation is in this direction. Is in this direction. Is in this direction. And this one must be in this direction. Got to be B sub Y. And this one, B sub Y. This one gonna be A sub Y. If you do the same calculation, summation F sub X equal to 0. A sub X gonna be 1.0. If you do the summation, let me zoom in, of the moment at A equal to 0, this one will rotate in this direction. Huh. It's going to be wrong again. This one rotate in this direction. So direction over here must be in the opposite direction. Let me put it over here. And also this one not correct. You just put it in the opposite direction. So take the moment over here. Rotate. This is gonna be positive. Okay. B sub Y. This is 5 meter times 5. Rotate in this direction about A. And then it's gonna be equal to 1. And then the distance from here to here, 4 meter times 4. Again, this is going to be 0.8. And you can see it's only in the opposite direction. Okay, and then if you do the same, summation F sub Y equal to 0. That one is positive. A sub Y gonna be 0.8. And then again, if you cut it for x1, okay, if this is gonna be x1, you have the force in the opposite direction. This is gonna be 1, and this is gonna be downward for 0.8. And now you are gonna have this one M1. Your M1 in this one gonna be minus 0.8 x1. Okay, just the opposite direction due to the opposite force. And let me zoom in. You have this one cut this portion, and this is subjected to 1.0, and this is 0.8. So this is gonna be your M2. Now, this is gonna be opposite direction. This is X2, and this is gonna be positive X2. Now, your F sub BB will be equal to integration. This one 0 to 5 and you have minus 0.8 x1 square. This is going to be the term for this one, the x1 over EI plus this one 0 to 4 and the term over here gonna be x2 square dx2 over EI. Just do the integration. You should have this one positive 48 over EI. So the deformation gonna be in this direction. Okay. And then let me zoom out. You are ready for the information over here. Okay. Just plug this one. You get this one for 3.333 over EI. Okay. Now, the next step, you may come over here, step number 4, determine the redundant force. Redundant force B sub y equal to following the equation over here is going to be 333.33 over EI and then divided by F sub BB. That's going to be 48 over EI. Cut. You got to get B sub y. I get this one to be 6.94. Let's check. That's going to be 6.94 kilonewton. And then it's going to be in this direction, 6.94 kilonewton. And this is going to be 6.94 kilonewton in this direction. Okay. When you get this, it's going to be your 6.94. Then you may move up to these pictures. Okay. You may determine A sub X and A sub Y. So, basis upon this one, you got to select a space. Let me go to the step number 5. You determine the reactions. We're gonna determine the reaction for A sub X, A sub Y, and B sub Y, and draw shear diagram, M diagram, and elastic curve. Let me take you over here. Okay, let me find the reaction. We have the frame 5 meter, and then we have this one for 4 meter, subjected to 16 kilonewton. 16, this one 16 kilonewton per meter. Let me zoom in. You get the redundant force to be 6.94 kilonewton. Then we determine again B sub Y, and then this one for A sub X and this one for A sub Y. Okay. Summation F sub X equal to 0. So basis upon this picture, A sub X gonna be 6.94. Okay. And then if you summation moment about A equal to 0, B sub Y rotate in this direction. B sub Y, the line of action over here, time 5, rotate in this direction. And then this one rotate in the opposite direction 6.94 times the distance of 4. And then we have this force of 16 times 5 rotate in the same direction of this force. So it's gonna be 16 times 5. Over here gonna be 2.5. So that's gonna be 2.5. And then you got to get B sub y. อาจารย์ get it to be 45.6. You get it 45.6 45.6 kilonewton. This is 45.6 kilonewton. And then if you do the summation F sub y equal to 0, okay, A sub y plus 45.6 gonna be 16 times 5. A sub y gonna be 80 minus 45.6, and I get it to be 34.4 kilonewton. Okay. Now, let us review what we should be able to draw the shear diagram and moment diagram. Okay, let us review it. And before I start to draw the shear and moment diagram, let me stop the zoom. Now, we got to separate the beam and the column, and the joist over here has no forces applied on this point. So based on what we learned, this one gonna be 5, 1, 2, 3, 4, and 5. Okay, that's gonna be the beam A, and that's gonna be C. And then we have this portion to be 5 meter subjected to uniformly distributed load 16 kilonewton per meter, and this portion subjected to 6.94. This one 6.94 kilonewton, and A sub y over here, that's gonna be 34.4 kilonewton. Okay, and then we have the joints over here, and this is gonna be joint C, and then we have the column, and that's gonna be 4 meter, and the column subjected to B sub y 45.6 kilonewton, and again this is gonna be the reaction of 6.94 kilonewton. Okay, so based upon this one, if you consider this portion, okay, you may see you should have this normal force, and you don't need to do the calculation. You can see this is going to be 45.6. That's going to be 45.6 kilonewton. And then over here, you should have the force going to be downward. Since this is upward, so this going to be 6.94 kilonewton. Okay. And then also, if you take the moment over here, summation of the moment about C over here, you should have this kind of moment M sub C. Okay, you should have M sub C rotate in this direction. And then you have 6.94 equal to 6.94 times 4. Okay, that's gonna be 27.6. That's gonna be 27.76 kilonewton, 76 kilonewton meter. Okay. And then following this 6.94, you should get this force in this direction and 6.94 kilonewton. And following the moment here, over here, you should have the moment rotate in this direction. Now, let me zoom in. Basis up on 6.94. You got to have the normal force over here and also over here. This one gonna be equal to 6.94. So take it, and this is 6.94 kilonewton. And then basis on this moment, you got to have this one to be the moment 27.676, and you should get this one to be 27.76 kilonewton meter. And then 45.6 upward, this is gonna be 45.6 kilonewton downward, and then you have this one to be 45.6 kilonewton. Now, you are ready to draw the shear diagram, moment diagram, normal force diagram for the beam here. So let us start with the beam, and let's put this one to be x meter, 0 and 5. You have this one to be the V kilonewton, and then 34.4. Okay, if you do the scale, 100 kilonewton per 10 millimeter, you may have this one to be up to 3 millimeter, 34.4. Now you come to this one, dv by dx gonna be minus 16. And then, this is gonna be 45.6. Okay, so this one supposed to be negative. Okay, this one gonna be negative 45.6. How Ajahn know it? Because the shear force over here is gonna cross this one up. Okay, that's why I noted minus 45.6. And then we have the linear slope of minus 16, and this is gonna be the point of zero shear, and this point you can determine it by the slope. So 37.4 divided by x is gonna be 16. So x is gonna be 34.4 divided by 16. I got this one. 34.4 divided by 16. 2.15 meter. Okay. When you get 2.15 meter, you will get this one to be 3 point, sorry, 2.85 meter. Okay. Now, coming to the next portion of this one, again, we have this one for x meter and this one for moment in kilonewton meter. And this is this one. Okay, take this one. How come? Got to turn off this one. Then take this one. Okay, it's come. This is pin. No external moment. Since this is no external moment, this is gonna point of zero moment. Okay, and we start here from 0 to 5, and we have the point over here. The point over here have what? No slope. Okay, we have dm by dx over here to be plus 34.4. But for over here, dm by dx gonna be 0. What gonna be the moment over here? M over here minus over here 0. And then it's gonna be 1/2 of 2.15 times 34.4. And you should get the M over here to be 36.98 kilonewton meter. Okay, and let's put it to be 50 kilonewton meter per 10 millimeter, and that's gonna be 37, and that's gonna be about 7 millimeter. It's gonna be somewhere over here, and the curve must be up like this one. And you know the moment over here 27.76. This is positive or negative. You may cut it over here. Okay. And then this is 27.76. You have the positive sign convention. You have moment M about this point plus 27.76 equal to 0. So this is going to be negative, okay, of nearly 5 point something millimeter minus 27.76. Then this is clockwise. It's going to take this one up. Okay, this is clockwise. The same concept as the shear over here. It's going to be negative. Since this one take up, okay, this one also clockwise positive. So you have this portion to be curved like this one. And then put the slope over here to be this value. dm by dx gonna be minus 45.6. Then this is shear force diagram SFD. This is BMD. For the normal force diagram, let me put it to be N in kilonewton. This is X meter 0. Sorry, 5 0. This is what? Compression, right? 6.94. So the beam gonna be subjected to negative normal force. That's gonna be the same for every section. Minus 6.94 minus 6.94 constant. That's gonna be N diagram or normal force diagram for the beam. Now, let me rotate it a bit, okay? You may follow this one later. Let me put it in this direction for our column. The column subjected to the shear force, yes. The normal force in the beam change to shear force over here. Let's put this one into V, kilo Newton. And yes, that is what, oh, take this one out. My hand may touch something over here. And then coming over here, we have 6.94, the same. That's going to be upward. Okay, and then positive 6.94. And then there is W equal to 0. dV by dx equal to 0. That's going to be positive 6.94 for our shear force diagram. And then for the moment, diagram. Let me put it again. That is gonna be x meter, and this is going to be moment kilonewton meter, and this is 0, and then 4. This is pin. Again, pin has no moment. And come over here, 24.46. Okay, this is what? This is going to be negative. It's going to take this one down. Okay, this one going to be 27.76. Ajahn, I won't believe it. M over here minus 0. It's going to be the area here. It's going to be 6.94 times 4. Okay, M is going to be the same. 6.94 times 4, 27.76 kilonewton, and it's going to be positive. Another thing you got to know, dm by dx is positive 6.94. Slope is positive. Then the moment over here must be positive. Okay, the confirmation. Okay, you don't need to do this calculation. Just take a note on the slope. Okay, and then you get this one, the last one, the normal force x meter, and this is going to be bending moment diagram, and then the compressive force over here is going to be 45.6. Okay, it's large, so this is going to be minus 45.6 minus 45.6. Now, you get your bending moment. Bending moment will help you to draw the elastic curve. Let's put it concave upward. Oh, sorry, this is here. Concave upward. And over here, concave downward. And this is going to be the point of 0 moment. Okay, let me take you over here. Concave upward, and then going back to be concave upward. So over here, there is a point of 0 moment over here. Okay, inflection point. So over here, you should get the deflection something like this one, concave upward. And then this portion, you got to have it to be concave downward. Okay, concave upward, concave downward. And this is going to be your inflection point. Okay, some people said it's going to be IP. Now, over here, it's going to keep the right angle. Okay, it's going to be something like this one, the 90-degree angle. And then come to this portion. This is going to be positive, right? And the curve must be something like this one. So the curve going to be something like this one. Okay, and then you got to show Ajahn. This is gonna be what? Zeta sub A. And this is gonna be what? Oops, sorry. The tangential line. This is gonna be zeta sub B. And then reference to this one, you may draw that tangential line over here and show me the direction from the origin to this one. This is going to be zeta sub C. And you should say V or delta sub C H equal to 0, delta sub C V equal to 0. No axial deformation of the beam. No axial deformation of the column. Okay, it has, but it's very small, infinitely small. Okay, that's why we said it's zero. Okay, and then you may put the steel reinforcement if Ajahn just take the area over here. I don't have much area. Let me take this one for the beam. Let me take this one for the beam and take this one for the column. Then you said this is going to be the elastic curve of what? Positive moment, right? So on this portion, you may put the reinforcement like this one to taking care of the tension on the bottom. And this is going to be your inflection point. Most of the time, you got to have this one called development length. Okay, passing the inflection point and hook it. Okay, to have a good bond, a good bond between the concrete and the steel. And also for this top portion, you may put this one. This is negative moment. And then you have this one. Okay, this one for taking the negative. And for this one, you have the tension on this surface. So just put the reinforcement, something like this one. Sometimes you may connect it together. Connect it together. Make it one piece. It's going to link. Okay, you don't need to hook it. It's going to work together. That's going to be the steel reinforcement. Okay, and this is going to be one of very complete problem that you may have. And let me move you to the next example of this one. Okay, I don't have much time. And for the next one, come to the problem over here. This one have a special thing. Ajahn provide you with the primary frame. That's another tactic. You got to know it. Again, the same thing. This is what? This has two EI, not only one EI. Both of them have two EI and two EI. Now, coming in this problem again, we're gonna select the redundant force. The problem didn't say anything about the redundant force, but it said a proper redundant force and provide you with this primary frame. Okay, basis upon, again, you may refer basis on the principle of superposition. We have this one plus the other frame, right? If this is the given primary frame, another one, take this one about this one for the beam BC, and this one for the column. And then you can see at the point A, this is going to be fixed end. Okay, so actually this is going to be your frame that's going to subject that to this C sub Y redundant force. Okay, so basis upon this one, this frame will have this kind of deformation. Okay, and then you just put this thing. This is going to be delta sub CV. Okay, and then in reality, you got to know that this is not really correct. But deformation over here, let me last it to make it more detailed. Actually, the horizontal displacement here and horizontal displacement here must be equal. Okay, so the projection from here to here, again, we have gonna be delta sub CV. And from our midterm examination, this one also has the slope over here to be theta sub C, but we didn't care about it. Okay, this is gonna be delta sub C H. Okay, over here, and delta sub C H gonna be equal to delta sub B H. This is delta sub B H, and delta sub B we gonna be 0. Okay, you don't need to write the pencil. Okay, but this one is required. And then basis upon this one gonna move up. Okay, for following this one, it's supposed to move like this one, and then this one should have this kind of elastic curve. Dock it. Okay, and then second, 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 second of what? We're going to write the compatibility condition. Basis upon this one, we have this is going to be what? F sub C C and time C sub Y. Okay, because C sub Y is unknown. We set C sub Y equal to 1. This is going to be F sub C C C sub Y. And again, this is going to be F sub C C C V. This is C V C V. Don't worry. This is C H C H and C sub Y. But we don't use it. We only use the vertical displacement, the same one as this one. So by consider the elastic curve of the frame we have the compatibility condition at C. Okay, at C. By putting this one, we have what? This is gonna be 0 equal to this one gonna be downward. You said positive. Okay, let's put it delta sub C V, and then this is upward negative F sub C C, and then C sub Y. Now putting this one, C sub Y gonna be this one 42720 divided by EI, and then you have this one to be F sub C C. Okay, the problem come to the point to determine F sub C C. Okay, Ajahn may change the problem. Okay, this one you got to determine F sub C C, but Ajahn may provide you F sub C C in order you to determine delta sub C V. That's going to go back to your midterm examination, right? Right? Okay, just rotate like this one. Now, the problem comes to the next step, the third. You determine F sub CC by using the virtual work method. Okay, the virtual work method. And then write the 1.0. 1.0 gonna time F sub CC. F sub CC. So you don't have another frame like this one, and that's gonna be subjected to the load of 1.0 unit. Let's say just put this one to be 1.0 and this gonna be provide small m. Okay, that's gonna be equal to integration of the small m. And this one is what? This one capital M. If you compute based on C sub y, since C sub y set to be 1.0, capital M change to small m. So this is going to be small m dx over ei. Okay. And now come to the point. Okay. It's up to what you're going to set for this one. Okay. And let me put this one to be your your x let me put this one to be x1. Okay. And you know, setting this one x2 gonna be convenient, right? Why is convenient? Because you don't need to determine the reaction. Okay, just take this portion and then this subjected to 1.0 and let's put this one to be m1 and then you should have m1 equal to x1. Okay, m1 equal to x1 and then for this one cut it over here you should have this is your free body diagram and then subjected to 1.0 and this is going to be your x2. Okay, and then if you said this is going to be your small m2, this is gonna be 8 meter. Okay, if you put it in this direction it's gonna be minus 8. Okay, the same direction, minus 8. And then you have this one to be equal to integration of x1. Okay, from here to here of 8 meter from 0 to 8 and this one gonna be your x1 square dx1 over 2 ei. 2ei. Don't forget 2ei, not ei there. Don't ei. 2ei. Okay, read the problem statement. It's so clear. And then plus for this one, you integrate from the top of this one and down to this one. That's 10 meter. So integrate from 0 to 10. And this is gonna be minus s dx2 over 2 ei. Okay, and then you should get the f sub cc equal to this is gonna be x1 cube over 3 and from 0 to 8 plus 64x2 from 0 to 10. Okay, you should have this one to be 170 point what 6 what 67 divided by 2 ei plus 640 divided by 2 ei and then you have this one to be 405.33 over ei. Okay, and it's gonna be upward. It's gonna be upward. Up. It's gonna be upward like this one. And then next step gonna be determine the redundant force of C sub y. Determine C sub y. C sub y again is gonna be equal to 4 to 7 to O over EI. And then this one 405.33 over EI. Cut. C sub y gonna be 105.4 kilonewton. Okay, you get the C sub y. Now, you just take the frame over here. The frame over here. Okay, so the next step, you are determine the reactions and the shear diagram, those kind of things. Okay, the shear force diagram, bending moment diagram, and elastic curve. Okay, elastic curve. Now, your frame is gonna be the frame subjected to the 20 kilonewton per meter, and then the column over here subjected to point B 60 kilonewton, and C sub y is gonna be over here for 105.4 kilonewton. And then you have the reaction over here to be A sub X and also A sub Y, and the moment over here for M sub A. And then this is gonna be 8 meter, 10 meter. You guys should be able to determine the reaction. Summation of X sub X equal to 0. A sub X gonna be what? A sub X gonna be 60 kilonewton. Okay. And then you may do the summation of F sub Y equal to 0 upward is positive. A sub Y plus 105.4 equal to 20 times 8. So A sub Y is 160 minus 105.4. So A sub Y is going to be 54.6 kilonewton. Okay. And then you may do summation of moment about A over here equal to 0. Take this is positive. M sub A rotate in this direction plus 105.4 rotate in the same direction. That's time 8. And then it's gonna be equal to 60 times 10 rotate in this opposite direction. And then this is 20 times 8 rotate in this direction. 160 over here is 4. M sub A gonna be 396.8 kilonewton meter. Okay. And for shear force diagram, bending moment diagram, elastic curve, let your guy do it by yourself. Okay. And you may assume it, guys. Let me take you to this one. You don't need actually the bending moment diagram. If you set this one to a fixed end, right? And for the force here, this one supposed to be moved over here, right? If this one move by 8 millimeter, the C also required to move by 8 millimeter. And you said this is going to be what? Delta sub CH equal to delta sub BH. This one, delta sub BH. Okay. And then since this is fixed, and then it will move like this one. It's only move like this one. No, it won't move like this one because this is the beam. So it should be moved something like this one due to the rigidity of the beam. If there is no beam, it will be something like this. But the beam have rigidity. So this one will have this kind of deflection. And then due to the rigidity, it's going to have this thing. Okay. If there is no rigidity, it's going to be something like this one. Okay. And then due to the rigidity, this portion will keep the right angle. And for sure, this one supposed to have this kind of deformation. So this gonna be the elastic curve, and then delta sub VV gonna be 0. And then over here, you should have the slope zeta sub V, zeta sub C. Okay, that's gonna be the elastic curve. And I got to stop my Zoom due to the limited time. No? Okay, let's stop it. Okay, class, let me move you to the next topic. We gonna study the statically indeterminate task, and อาจารย์ should show you some pictures. On this picture, there are the construction of I like to cross this. How come it's one cross? Okay, this one. This picture show you the task of the roof of the digital building. I don't know at the time of building of the digital building you have studied already or not, but I don't think so. That's about 4 years ago. And this is on the roof. Okay, the task is pretty big. They use tower crane to hold the task into the position. The task here is statically indeterminate task. Now, I like to take you to the task of the roof of this building. Okay, one, you may assume it to be pin and roller. If you assume it to be pin and roller, the task gonna be statically determinate. Okay, and if you assume the support of the task to be pin as this one, now the task on the bottom picture is gonna be statically indeterminate task, and this task gonna have degree of indeterminacy equal to 1. Okay, you can check by yourself. Okay, between what? Between B plus R, and then compare it with the 2J. That means what? You are as the engineer. You are the one who assigned the support. You are the one who said the task gonna be statically determinate or statically indeterminate. And then if you do the model of the task following whatever, you got to provide the detail of the support as your design. Now, the task also can be more indeterminate, such as you may put the column at the bottom of the task in order what? Enhance the strength of the task. Okay, if the task have large deflection, just pop up. You know pop up, right? Just put the column and then push it back. You increase this one. So now the OI gonna be changed to 2. That means it's up to what you modify the structure also. Okay, you also can increase the degree of indeterminacy of the task. Like the second one, you put 1, 2, 3, 4 more members. The task gonna be stiffer. Okay, the task gonna be more stiffer, but the degree of indeterminacy of this task gonna be 4. Okay, equal to number of
members you add into the Truss. Now, in conclusion, okay, the degree of the indeterminacy of the Truss can check from B plus R. This is gonna be the number of the unknowns. Okay, it's gonna be the number of bar plus reactions, and then compare it with the term 2J. You know, each choice of the task has two equation. Okay, so two equation times number of choice. This going to be number of equation of equilibrium. Now, you can use the knowledge from chapter 3. Check the degree of indeterminacy of each task. Okay. And now, oh, I forgot to tell you one thing. The indeterminacy of the task can be classified into two types. One, we call it internal indeterminacy by adding the member into this one. You cause the degree of indeterminacy by adding internal member. Okay. And also, if you notice this one, you can make the task to be indeterminate by changing this one, by changing the support, or also by adding this one, by adding more support. The way we do it over here, this one opposite to this one, this adding internal member causing indeterminacy. This one adding external support to make the task indeterminate. Okay, two things. Adding more member, that means you make the task indeterminate by adding more member. This kind of external factor. The one over here is a kind of internal member. And then the problem that we're gonna solve for the statically indeterminate task can be classified into two things. That means one for internal degree of indeterminacy. Another one is gonna be external degree of indeterminacy. The problem here, we have this is pin. This kind of problem can be classified of indeterminacy due to the adding external support. Okay. And then let's say the task has constant EA, axial stiffness for all member. We start by what? Checking the degree of indeterminacy based upon this one. The task will have A sub Y. We have B sub Y. We have what? B sub X and also has A sub X. You got to select which one gonna be the redundant first. Okay. The problem said the task is statically indeterminate with one degree of indeterminacy due to the extra support. And then if you select this one as the redundant, again, use the principle of superposition, separate this task into two more tasks. Okay. Now, use B sub Y. Sorry, I'm wrong. Not B sub X. Use B sub Y as the redundant. Now, the support over here must change from what? From pin to be the roller, and then you got to put the redundant force over there. Now, you separate the task into two tasks. The first task called primary task subjected to external force with what? With the roller over here. And another task have the same roller, but it's subjected to the redundant force. So the task on the left is going to be equal to the task on the middle plus the task on the right hand side. Now, you got to use your knowledge on elastic curve to assume how the task deform. Okay. And then for the task subjected to R sub by. R sub by is unknown. Okay, this is unknown. You got again set R sub by to be 1.0. And then if you set R sub by to be 1.0, the deflection over here gonna be the deflection at point B due to the 1.0 unit load at point B. Over here supposed to be F sub BB times the redundant force. Now, you may use your, you may write your compatibility. Now, it's going to be at point B over here to be 0 equal to this one going to be delta sub by. This downward positive. So this R sub B times F sub BB also downward. So this is going to be positive. Now your equation going to be R sub by equal to negative delta sub by divided by F sub BB. Go back to chapter 7 to determine the displacements. Now, for the delta sub by, you got to use the method of virtual work. Now, basis on method of virtual work, you got to put 1.0 over here. 1.0 gonna cause what? Gonna cause the internal force on the task to be small n. Okay. And the pictures over here is going to be what? It's going to be the task with this one to be the roller. This one will determine the capital N due to the actual force and going to provide the real actual displacement delta sub by. Now, it's come to the point you got to use the knowledge determine capital N. Okay. And then basis upon your knowledge, you got to notice the task with zero force member, and you can see the member over here is gonna be zero force member. And also you have the BC. BC is what? This is going to be the member. Has zero force also. Okay. And then after you determine capital N, you got to put 1.0 at which point? At point B. And then that's going to be in this direction. And do the same calculation for small n. Okay. You can compute small n, capital N times L. And then you get the result to be 135. And you got to get 135 divided by AE. And it's positive. That means it's going to be in this direction. You get 135. And then I should say downward. Now, for the small F sub BB, okay, actually, this one, you set B, sorry, R sub by to be 1 kilonewton. Okay. Actually, this one provide us with the capital N, but you set it to be 1 unit. So this is going to be small n. And the same thing occur for the frame. Okay. When you determine small f sub bb, you got to get the term like this one. Okay. Before that, you get small m square, right? For the task, you got small n square. Use the same n that you have from the previous slide, the end over here. You didn't need to determine it again, right? Just use it and put it into the equation. You get n square L to be 23 divided by AE. Now, this one also downward. And then you put it back. Okay. You got to have this one to be negative. That means what? The direction of the redundant force is not correct. You got to change it again in upward direction. Before that, you said it's downward, right? And then you get negative. So this, the correct direction gonna be upward. Now, you got to determine the reaction. And then after you determine the reaction, you may use method of choice or method of section to determine the force in each member. That's going to be the whole process. Ajahn, that's going to be a lot of work. Don't worry. Sometimes Ajahn give you the capital N. Okay. And also small n. But you got to think about the process. The process going to be the same. Okay. Thinking about the process. And then you get the internal forces for the truss member. And then you may draft the elastic curve of the truss also. Next, we have this one pin, this one roller. Ajahn, I can determine the reaction for this truss. Yes, you can determine the reaction for this truss. You may determine A sub X, B sub X, and also A sub Y. Summation of the moment about A to be 0. You have B sub X rotate in this direction. B sub X gonna time this one 4. And then it's gonna be equal to this one in opposite direction 10 times 3. So B sub X is going to be 10 times 3 divided by 4. That's going to be 7.5 kilonewton. This one is going to be 7.5 kilonewton. Summation of X sub X equal to 0. A sub X gonna be 7.5 kilonewton. And if you do the summation of F sub Y equal to 0, A sub Y gonna be 10 kilonewton. Okay. This one is the task going to be DOI equal to 1. By what? By adding more member. You know that typically simple task gonna have triangle, okay, shape. But this one, you have one more internal member. Since it is internally indeterminate, you got to select a proper redundant force. Previously, we used reaction as the redundant. Very important. Okay. Previously, you used the reaction to be the redundant. But this one you cannot. Because all the reaction you can determine, you got to select one of the member force to be the redundant force. You take F sub AD to be the redundant force because there is no choice to select the reaction. Okay. This is the main point for this kind of task, okay, use the axial force in the member as the redundant force. Now, thing gonna be the same. Use the principle of superposition. Okay, draw two more tasks, but that task will has no member AD. Okay, you got to take the member AD out, cut it. Okay, cut it, no member AD, and then you got to put the F sub AD as the redundant force. Now, the imagine of the elastic curve gonna be very complex. Okay, most of the time they didn't write the elastic curve. It's gonna be tough, but you got to know that the primary structure gonna have the formation or the displacement in the AD line, and we call it delta sub AD. And for this picture, for sure, delta sub AD gonna be elongation. Okay, and then if you said AD is in tension, AD is in tension, gonna be positive, right? So the force here gonna change to this one, and the force here gonna change to this one. Okay, the force, the force, the force over here at the point gonna be in this direction, and the force over here gonna be in this direction. Follow third law of Newton. Now, this problem gonna be a bit more complicated than the previous one in the determination of the displacement delta sub AD, and this one F sub AD, the axial deformation, okay, along AD due to the force along AD, like F sub AB, the deflection at point B due to the unit load applied at point B. The deformation along AD due to the unit load applied along AD. Now, based upon this one, again, you got to write the deformation on this member AD gonna be very small. Set it to be 0. And then this is positive. Okay. This gonna be positive. And this deformation due to the tension, you got to put it to be positive. This is gonna be elongation. Okay. And this one also in this direction. And now you got to determine the displacement delta sub AD and F sub AD. To determine this one, you use this equation. You got to put 1.0 unit load in this direction, and that's gonna provide you with the small n. Okay, so this one you calculate for capital N. For sure, the force over here, if you cut it, this one F sub AC gonna be 10 kilonewton, and this is gonna be 0. And 10 kilonewton here gonna apply over here. Then you can determine the force in this two member, and then you have the force BD equal to 0, and the force in member AD, sorry, AD is over here, got to be 0. Okay, AD have no member, so the force in the member AD gonna be 0. But you got to put AD into the table. You cannot neglect it. Now, for the small n, you put the force n over here. This is important. Okay, in the AD. And then you determine all the internal force. Then you have small n, capital N, L. and then you have this one to be negative. That means what? Actually, it's going to be in the opposite direction of what? Of this one. Of intention. It's going to be in the contraction. Now, for this, oh, sorry, this is going to be elongation, not be, this one is going to be in the contraction, right? The unit over here, opposite to this one. This one gonna move AD close to each other, gonna be contraction. So negative gonna be elongation. It's move AD closing to each other, but in the opposite, it's gonna be elongation. Now, for one unit load, you have the same thing as I explained before. This one will provide you with the small n, and you determine F sub A D in this line subjected to unit load in the same AD. And then following this one, do the same N as before from the previous slide. And for sure, Ajahn will provide you with some capital N and small n as the previous midterm examination. You get the result. This is what? This move in the same direction as one unit load. Okay, to make it shorter. Move in. Okay, and then you put everything together, and you got to get this one to be 8.102. That means AD gonna be 8.102. You cut this joint, determine the force here and here. After that, you cut this joint, determine the force in the member. You can determine all the forces in the Truss member. And that's going to be all for this one. We have the composite structure. That's going to be in the form of beam and pilot. Okay. And it's going to be out of the scope of our study. But Ajahn have the PowerPoint for this one. If you prefer, you may study it by yourself. Another method that we have called method of least work is going to be the same concept as the consistent deformation. But instead of using what's so-called the redundant force, they use the mathematics to do the computation. That's one also assign you for self-study. So for today, I finish my lecture on the frame and on the truss. However, I will add more example for the truss into this video clips. And next time, we will have 2 more example on the truss. For the frame, Ajahn, I already added more example for the beam and more for the frame. Okay, so you can do the study by yourself on the video clips. Okay. Anyway, anybody have question? No question as usual. So have a good day. Bye bye.
This truss has the picture here. It has the roller at C, has the pin at A, and also has the pin at E. So by this formation, this truss is going to have the reaction of 5, 1, 2, 3, 4, and 5. And this truss has 1, 2, 3, 4, 5, 6 members. So the truss gonna have the unknown forces and reactions. Each member gonna have one unknown of internal force. Okay, and the reaction at 5. So we have this one of 6 bar plus 5 reaction. So the unknown is going to be 11. And how many equations do we have? Each joist of the truss, which is the frictionless pin, are going to have 2 equations of equilibrium. And when you time the number of joists, you're going to have the total equation to solve this truss. We have 2 times 1, 2, 3, 4, 5 times 5. That is going to be 10. Now, what we have, the degree of indeterminacy is going to be 11 minus 10. That is going to be 1. So this truss is going to be statically indeterminate truss with the degree of freedom equal to 1. Now, we're going to set up one unknown force as the redundant basis on the consistent deformation, and most of the time the redundant going to be kind of an isolated force. So this time they set the C, the reaction at C, as the redundant. So if they set that, so our C sub y gonna be the redundant. And now when you put the C sub y as the redundant, you will take the roller out, and then you put the reaction at point C, which is the redundant, act at point C. Now, so first let the C sub y as the redundant force, and second, okay, we're going to find the compatibility condition at C in y or vertical direction. Now we're going to do what? We're going to use the principle by using the principle of superposition. We can separate the truss into two cases. Now we're going to separate this one. The first truss is going to be the primary truss. This is going to be the primary truss, which is subjected to P equal to 10 kilonewton. So this is going to subjected to the giving force of 10 kilonewton. This truss has the stiffness of 20,000 kilonewton meter square per square meter. So all of them have the same stiffness, and this is going to pass, okay, pass another truss that's going to subjected to the redundant. So this is going to be another truss, and is subjected to the redundant. So this is going to have the pin and has the free, okay, at point C. So at point C, this is going to have the C sub y, and when you separate into this one, this is primary truss subjected to the given load. This is going to be the truss subjected to the redundant force C sub y. Okay, and what happens is, under the application of the force, the primary truss will deform like this, and this truss will deform by this point, gonna move from C to C prime, and the truss supposed to have the deformation, okay, upward like this one. And what we have is, this is going to be the deformation, the vertical deformation at C. Since C sub y is unknown, usually we just set C sub y equal to 1, and this is going to be the deflection at C in the vertical direction if you like. Okay, when the force applied at C. And if the total force is C sub y, so the total vertical deflection gonna be F sub CC C sub y. Okay, by considering the deformation of the truss, okay, and the vertical displacement at C. So we have what? We have this one 0, and let the downward is positive. This is going to be the delta C, and then it's going to be delta the deflection at point C in the vertical direction, and it's going to be minus, this is upward, F sub CC and C sub y. So your C sub y is going to be delta sub C divided by F sub CC. And the problem gives us the deflection over here of 9.761 millimeter downward. So by doing this, actually we can determine it 9.761 millimeter and divided by F sub CC. This is going to be the compatibility condition at C in the vertical direction. And now the problem is we got to define the deflection, right? So the third 1, 2, and 3, we determine the force displacement relationship. Actually, this one is only F sub CC by using the what? By using the method of virtual work. Okay, if you use the method of virtual work, and let's see if you like to determine this, we got to what? We got to put one unit force act in the same direction of F sub CC. So that means you're going to push this one at point C by 1.0, and then this 1.0 times this real displacement. So it's going to be the what's so called the external virtual work. That is going to be equal to internal virtual work, and external virtual work is 1.0 time this one time F sub CC, and it's going to be equal to this 1 unit of applied force produce the internal force of N, and this N is time the deformation here. Okay, the deformation here also can determine from the elongation or the shortening of this, and you know that the deformation or the shortening here can be determined from the Hooke's law, and it's going to be N over AE. Okay, and now what we have is this is going to be summation of small n, NL over E. It's going to have NL over AE. And what we have, since the C sub y is going to be equal to 1, so the n that's due to this one will change to small n. So this one is going to be the summation of n square L over AE like this. Okay, and this is going to be the equation for the method of Okay. And also, if you like to determine delta sub c, you do the same thing. This is 1.0, apply this. You're going to have 1.0 and then time delta sub c, which is going to be equal to summation. This is going to be n. Okay, n because of 10 kilonewton, then because of P equal to 10 kilonewton, so it's going to be small n and capital N times L over AE. Okay, and you also can determine this 9.761 if you put into this equation. Okay, anyway, we got to find n, so we set up the truss here and we are looking for the n. Okay, we have 5 centimeter, let's say for 5 meter for 2.5 centimeter. It's a scale like this, and this one is 4, that is going to be about 2, and this is going to be 1, so your truss is going to be like this. This is a pin, and pin, and you have this member and have the pin also here. Now, the truss is going to look like this. Okay, and the force of 1.0 apply here to determine n. So we going to find the force in the truss truss member, which is the n. Okay, this is going to be A, B, C, and D and E. This is going to be 5 meter, and this is going to be 4 meter, right? So this is going to be 4 meter. We're going to determine the n. Now, what is this? This is going to be 2 meter, and you also can determine the theta here. So the theta here is going to be 10 arctan of 2 over 5, which is going to be 21.8 degree. Okay, you can pause the video and try to check the number what we have here. And from this, we can apply the concept of zero force member. Do we have some zero force member here? So we have a zero force member. Okay, zero force member, we have F sub BD equal to 0. If BD is 0, see, this is going to be in the same horizontal direction. So you also have F sub AB equal to F sub, this is BC. Okay, that is a good thing of zero force member, is help you to reduce the calculation work. Now, we are here. Okay, we have this one for point C, we have this one for X, this one for Y, and 1.0 apply here. That is going to be 1.0 here. And due to this, what should be for this one? Okay, this is going to be downward, right? Because when you project this, it's going to balance the 1.0. And since you project this one, is going to take on the right. So this portion going to take on the left. And this is going to be F sub BC. And this is going to be F sub CD with the angle here of 21.8. And now you will determine this by what? By summation of F sub X? No, F sub X, you're going to have two unknown equations. So summation of F sub Y equal to 0. And then you're going to have this one downward. So downward is positive. You have F sub CD. You're going to project in vertical direction sine 21.8 degree. and then you get this one equal to 1.0. So your f sub cd going to be 1 divided by sine 21.8. That is going to be 693. Okay, that is going to be your f sub cd. So you get this one for compression minus 2.693. Okay, and another one, you have this summation of x sub x equal to 0, and this direction is plus. So you have f sub bc in this one, and it's going to equal to this guy cosine 2.690 cosine 21.8 degree. And now you just put into your calculator, you will get this one of 2.50. Okay, this is for f sub bc, and it's going to be in tension. This is going to be plus 2.5, and this is going to be 0. By doing this, this is also f sub ab equal to f sub bc. This is 2.5. So you got this one. This is plus 2.5. Okay, now you have two more member, DE and AD, right? So you put this here, and you have 2.63 here. This is going to be 2.693, and it's in compression. This is the joint of the dog. And then you have the force here. So I believe this one's supposed to be in compression. This is DE, F sub DE. Okay, and you have another one here. So this is up. So this one also point out right in here. That is F sub AD. Okay, and you may have this one theta. So this one gonna be theta, and this one also theta. Now you have the total of 2 theta here. You may use the x and y to calculate this, but it's not that convenient to set that x. It's better to set this one as x palm and this one as the y palm. Okay, if you set like this, this two going to be in the same direction, and this one can be projected into this direction. Okay, and oh, sorry for this. And then you have this. Okay, summation of x sub. If I do this, f sub y palm, f sub y palm equal to 0. This is going to be in this direction. Okay, and if you project this, this is going to be in the y palm. So it's going to be f sub AD, and this is cosine. This is going to be sine 2 theta, and this is going to be up, right? There is no force here, equal to 0. So your f sub AD is going to be 0. And if you do the summation of x sub x palm equal to 0, putting this one, you got f sub dE, right? So this is going to be f sub dE, and it's going to be the same as this. So it's going to equal to 2.69. This is 993. Okay, that is going to be f sub dE. So the dE is going to be minus 2.693. And this also be 0. The same thing as this one is 0. Now, you get all the forces that you may like to have. Okay, you have the member. You have the member. You have the member of what? you have the member, many member of AB, A, B, B, C, C, D, D, E, okay, and AD and BD. Okay, that's all you have for this member. And you also have the L, right? You also have the L. This L is going to be meter. L is meter. And if possible, please have the horizontal line to separate them like this. Okay, this is 5 meter. This is 5 meter. And this is 2 square plus 5 square. And square root of that is going to be 5.38. 5.385. And this is 5.385. And 80. 5.385. And this one 2.0. Okay? And the n. And the n. You have the n. Small n. Okay, this is what? AB plus 2.5. BC plus 2.5. Okay, and else, this is minus CD, 2.693. DE minus 2.693. AD is here, is 0. Okay, BD is 0. Okay, and then you may determine the n square if you like. This is n square. This is a plus 6.25 plus 6.25. This is also plus. This is also plus. 7.25, 7.252, 7.252. And this is 0, 0. Okay, and the last one, you may compute the n square L. You just time it, n square times L. That is going to be plus 0, 0. 31.25, 31.25, 39.05, 39.05. And then you get all of this here for the summation. That is going to be 140.6. And now you can determine the F sub CC. So your F sub CC going to be this n square 140.6 divided by AE. And this is positive, right? So it's going to be up. And this is in millimeter, if you like. This is going to be 140.6 divided by 20,000. And you also can see that this is going to be in meter. If you like to answer in millimeter as it was, it's going to be 3.03 millimeter. And this is going to be upward. Okay, that is the result that you may have. And if you prefer, you may do this from this equation. You can see the n is the same as we have the n here. But this one for the capital N, you can check whether what they give us is correct or not. Okay, if you have time. This is zero force member, zero force member, zero force member, and zero force member. So if you like, you will have this one for joint D subjected to the force of 10 kilonewton here. And what you have is 2 force here. You can determine it easily, right? So if you set this one is the X and this one is the Y, so I think this one should have this force here to balance it. This is going to be AD. This is going to be F sub AD. And this is going to be F sub DE. Okay, this is going to be F sub DE. And you may know that the angle here is theta, and this one also theta. Now, basis upon this, you may use what summation f sub x. You will get this one, summation f sub x equal to 0. You may have this one cos and cosine and cosine. So f sub dE will equal to f sub AD, since they're going to cosine with the same theta. Okay, f sub dE. So you got this is plus. And you may do the summation of f sub y equal to 0. So this time just up is the plus. So this one is up. This one is up. So S to F, let's say is F equal to F. S to F, up and up. And it's going to sine 21.8 degree. And it's going to equal to 10. Okay, so this one, the F is going to be, this is 10 divided by 2, like 5 divided by sine 21.8 degree. What do you have? 5 divided by 21.8 degree. Sine 21.8, sine, sorry. 21.8 and sine 0.3714. Okay, so 5 divided by 0.3714 is going to be 13.463. That is going to be equal to 13.163 kilonewton. That is going to be equal of this. Okay, if you like, you have in here, and you may put this one over here, and what you have is going to be only these two. This one is in completion, minus 13.14, sorry, 463, not 4, 463.463. This is plus 13.463. Only AD and ED and ED. Okay, so the DE is plus 13.463, and this is going to be minus the AD. Okay, 13.463. This is 0, 0, 0, 0. So only one that you have is this, okay, and this one, and it's going to be delta sub C gonna equal to, for the DE only, for this DE, 5.38 and minus 2.693 and time this one plus 13.463. Okay, and you may get this divided by AE. Okay, that is the total of this 13.463 times 2.690 times 5.385. Okay, that is 5.3 is 5. That is going to be 195.23 and divided by AE. And you're gonna divide it by 20. Okay, that is going to be 9.762. 61. Okay, that's it. So you have this one for 9.761610 minus 3 meter. This is good enough. Oh, this is good enough of 9.761 millimeter. And this is negative. Yeah, this one negative. This one is negative. So this one is positive. It's going to have the opposite direction of this. So it's down. So check. You got this result for what given over here. Okay. And now, what else you can do? You get this already. That's mean we plug back into this. We gonna determine. So it's 1, 2, 3, 4. We determine the redundant, D sub C sub Y is going to be C sub Y. And this is going to equal to 9.761 divided by 7.03. millimeter. And then you get this for 1.39 kilonewton. Okay, this is one of the thing we have, C sub Y, and the result is this. So now we may just apply to here. Okay, do the same thing. This is going to be the truss. Our truss, the free body diagram of our truss. Okay, what we have is the 10 kilonewton apply here. 10 kilonewton. And what we have here is 1.39. Okay, this is the A, B, C, D, E. To make it more complete, this is going to have the A sub Y, or we also have this for the A sub X. Okay, and this is 5 meter. This is 5 meter, and for this one, actually, is the pin at here, but it's connect directly to the member ED. So this is going to produce the force of F sub ED. Okay, this is going to be theta. And we may also have the E sub X and E sub Y if you like. This is a projection, this is a dashed line, okay? And what we have, this is 4 meter. Now, you got to determine the force, right? So you may take this one. This is going to be F sub ED cos 21.8 degree. This is going to be F sub ED sine 21.8 degree. If you do the summation of the moment about A equal to 0, okay, just take summation of the moment about A equal to 0. And you determine this, right? So just push it is positive. We have what? We have this one times 4. We have f sub ed cosine 21.8 degree. Have this time 4. That's counterclockwise. That is counterclockwise. And you have this plus 1.39, and this is 10. And you're going to have this one equal to 10 คูณ times 5, 10 times 5. And now you can determine f sub de easily. F sub ed equal to 9.72 kilonewton, and take it out. So this is the T. Okay. And you may say, if you project this one, so the E sub x is going to be this one, 9.72 and cosine 21.8. And you project this one is the E sub y. E sub y equal to 9.72 sine 21.8 degree. So you get the result. Okay, E sub x and E sub y. This is going to be 9.02. Okay, and you may have also for this one going to be 3.61. Okay, now you can go further to determine the a sub x and a sub y, right? We can do it easily. Okay, let's go further to find this a sub x and a sub y. Now, just put this one as the E sub x equal to 9.02 kilonewton. And this one E sub y, 3.61 kilonewton. Now, you do the summation of x sub x equal to 0. And now if you put this one is plus, so your A sub x can be easily A sub x equal to 9.02 kilonewton. Okay, and then you do the summation of f sub y equal to 0. What you get is this one, right? It's going to be A sub y plus 1.39, and this one plus 3.61, and then up. This one is downward equal to 10. Okay, and your A sub y gonna be 10 minus this is 5. That is going to be 5 kilonewton. Okay, that's for all the reaction do we have for this. Now, we're going to determine the force in the member. And if you notice between this one and this one, you can determine the F sub CD and F sub ED of this problem easily. Okay, by considering the free body diagram of the joint C. We have, if you do this, we have this one gonna be F sub CD. We have F sub CD equal to, this is 1.39, this is 1.39, and time this, time minus 2.693. And also one F sub BC, F sub BC equal to 1.39, and time this one, time plus 2.5. So you got F sub BC of 3.475, 3.4 BC 75 kilonewton, and it's going to be in tension. So this is plus 3.475, and this is going to be equal to minus, right? and it's going to be in compression if you like. 3.743. 3.743. This is going to be minus 3.743. Now, the concept of zero force member still apply. So this is going to be for zero force member. Okay, this is zero force member. Now, you just determine this, the force of this one and this one due to the 10 kilonewton. Okay, and then if you prefer, it's going to have the compression here. So now at point D, you have this one, you have this one, you have 10 kilonewton, 3.743. This is 3.743 kilonewton. And then you have two more of this. Let's say we have this before, right? When we determine the reaction at this point, it's going to be 9.72. So this is going to be 9.72 kilonewton. So only one that we gonna determine is F sub AD. This one is plus 9.72, and you have this one for F sub AD, and this is going to be 2 zeta, 2 times 1.8. You know that. Okay, it's up to you. You may take the consideration about x, y as before, or you may take this one for the x palm, and this one gonna be the y palm, and this one y palm. This is gonna be zeta. Okay, and it's better to take this one in the x palm direction. So summation of x sub x palm equal to 0. This one is in this direction is plus. So this one F sub AD, that's gonna cause 2 times 31.8, 43.6 degree. Okay, and this is going to be along this direction, and it's going to equal to 9.72. Right? It's going to be this one. This one is up. This one is up, and plus 3.743, and this one is going to be this one cosine, this one sine, minus 10 sine 21.8 degree. Okay, so now your F sub AD gonna equal to 9.749, and cosine divided by 43.6 degree, and you get this for 13.46 kilonewton. Okay, and this one is what? This one is compression. So this one is minus 13.46. So that's all we have for this analysis of the truss. We got the result of this, and then you should put this one into this table. Okay, and then you will have this one for plus 3.475 kilonewton in tension. This also 3.475 kilonewton in tension. And for the CD minus 3.743 kilonewton and in compression. And DE we know that 9.72. This is 9.72 kilonewton in tension. AD we just finished is 13.46 kilonewton. That is in compression. And the last one for the BD is 0. Okay, that's all we have for the analysis of this truss, and you may do it again by yourself. Close everything and try to solve slowly. Try to understand what actually is in this calculation. Try to understand, review your truss analysis that we take from the Static and the chapter 3, and don't miss it, because if you cannot use the knowledge correctly, the calculation here also going to be incorrect. Okay, do a lot of practice. Okay, end of the clips. We are going to study on the using of the consistent deformation method to analyze this statically indeterminate truss. This truss has the internal indeterminate, since it has more member in the BCEF interval. And if you consider this truss, you may see the A is the pin, right? So we may have this is A sub X and this is A sub Y. We can also determine this one, the D sub Y. And if you like, you may use the summation of F sub X equal to 0 for this one. And you can determine A sub X equal to 0, right? And also, if you like to take moment summation of the moment about A equal to 0, we have three unknown equations. We can solve it. This one, the D sub Y, like this. So we have the D sub Y times 9D sub Y. And then that is going to equal to what? 4.5 times 3. 4.5 times 3. And then plus 3 times 6 plus 3 times 6. And then you may determine this is 18. And then in this D sub Y going to be 3.5 kilonewton. So this is can be 3.5 kilonewton. And this is 0 kilonewton. And you do the summation of F sub Y equal to 0. So the A sub Y can be determined. It's going to be this one plus this one, 7.5. 7.5 minus 3.5, this is going to be 4 kilonewton. See? You can solve for the reaction. Not only that, you may also, if you take the A here and you cut the joint of this X and this Y, and this is what? 4 kilonewton. So you can determine the force in the AE and AF. The AE is supposed to be in compression, but because this one up, so our F sub AE should be here. F sub AE. And this one, when it's project, is from the right to the left. So this one gonna be in tension. This is gonna be F sub AB. And you may also know that this is gonna be what? 4 and 3. 4 and 3. Okay, again, based on this, which equation you going to use first? Which equation? I just want to solve some that we can determine, and then we will later show you the consistent deformation method. So which one is first? So this one, if you do the summation of X sub X, you cannot get the result, right? Because you have two unknowns. So you do the summation of F sub Y equal to 0. And downward is positive. So you get this one is the downward times 4 divided by 5. So you have F sub AE times 4 divided by 5. And then this one is down and this one is up equal to 4. So F sub AE will be equal to 4 times 5 divided by 4. So F sub AE is going to be 5 kilonewton. And this is in compression. Okay. And also this one you can do it easily to determine the summation of X sub X equal to 0. You get F sub A B equal to what? 5 times 3 over 5. 5 times 3 over 5. That is going to be 3 kilonewton. Okay, you can solve everything, and now you get this one plus 3, this one minus 5. And you may see what they're asking us. They didn't ask us for what I'm doing here. They asked us for the member BC, member EF, member BE. And after you know this, see, even though you know the force here, you cannot cut here and solve from these three forces, because we have only two equations, summation of x of x equal to 0 and summation of f sub y equal to 0. Okay, and also we cannot solve for this, but we also still can solve for this one, as you may have it before. This one you may put to 3.5 kilonewton. Okay, and then you may have the x and you may have the y here, and for sure you will have the compression here, and the force is F sub dF, and this one also must be in tension because of this. Okay, this is going to be F sub CD, and again you can do the same calculation, and then you get the force in this member. And if you do that, you may get this one for minus 4.775. It's going to be close to the same. Okay, you just F sub AE times 4 over 5 equal to 3.5. So it's going to be 3.5 times 5 over 4. You get this. And the last one, you get this one for plus 2.625. 625. Okay, and then you get all the answer of that, but not those in this region. This is BC. BC is here. This is CE. CE is here. Okay, this is gonna be EF. Okay, EF is here, and this is gonna be BE. BE is here, and the last one CF is here. CF is here. Okay, CF, and the last one is BF. See, they didn't ask us to determine what I just did to you. And how do you check this structure? Is going to be statically indeterminate truss, and it says internally. Internally is due to what I'm just explained to you. You check with what? B plus R. Okay, how many B? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. B is 10. Plus R, you have A sub x, A sub y, this y, 3. So this is going to be 13. And you got to compare with the equation you have. You have two equations per choice, and times the number of choice. So it's 2 times 1, 2, 3, 4, 5, 6 times 6. That is going to be 12. So the degree of indeterminacy, degree of indeterminacy, which is DOI, is going to be 13 minus 12. It's going to be 1. So this method, we need require one redundant force, and this redundant force must be the force in the truss member. It must be truss member force, because it is internally statically indeterminate truss. And they ask us, they give us the member CE as the redundant force. So this one, the CE is the redundant force. Okay, so okay, the redundant force is F sub CE, the first step, and the truss. the redundant force is CE, so the truss can be separate into two cases. Okay, so the truss can be lead all as show. Okay, after you do that, you read all the truss as show, and then you have what? You have the redundant force as F sub CE, so it's 3. Okay, and then your truss is 4 meter, it's about 1.33. And what happened is this is going to be the same. It's going to be B F E C, and this is B A E, and this is going to be F D. And your task is going to be something like this. After you're going to use the redundant force as F sub E, so the member CE, you just take it out. Your structure will change from the statically indeterminate to statically determinate. However, you have this as the unknown. F sub CE apply to your structure with respect to the giving load of 4.5 kilonewton. And this one is 3 kilonewton. Okay, that's what we have for this one. And then what you may have is to set the compatibility condition. So next one, we will compatibility condition along CE line. Got to set this along the CE line. Okay, and then we use the principle of superposition to separate the truss into two cases as shown. Okay, so we have one is the primary truss. So this is going to be equal to and then you're going to plus another one. One truss will subjected to the applied loading, and the another truss will subjected to the redundance, and when they combine to each other, you will get the statically indeterminate truss, and then you can solve from the force displacement relationship. Okay, the first one will subjected to the applied force, and we call this as the primary truss. This is 4.5 kilonewton, and this is 3 kilonewton. And again, this may call the primary truss, which is the same as here. This is primary truss. Okay, that is going to subject to the giving load, and we have another truss here. This is the truss subjected to F sub CE. Okay, so this one we put F sub CE into the truss. This F sub CE, and this is F sub CE. Okay, and now we consider what use the principle of superposition to separate the truss into two cases as shown. Okay, by considering the displacement along CE line of the trusses, we have have what? Under the application force, this one will some deformation, okay, but this one may also have their own deformation. The point E C will change, okay, its length. Usually it is 4 and 3, that is 5. Okay, now it's changed to C palm and E palm. So the line used to be, this is 5 meter. It is going to change to this line. Okay, and then we can subtract the length of this blue line to the length of this red line, and then we said this is the delta along the CE. Okay, it's the change of the length along the CE line before the application of the force compared to after the 4.5 kilonewton and 3 kilonewton applied to the truss. And this one also, when it's subjected to this force, this point is supposed to be moved. Usually it's the CE is going to move to C palm and E palm. Okay, and we said this is going to be F sub CE CE when the force, the latent force is 1.0. And if you time it by the total of latent force, so the total deformation or displacement at this truss gonna be F sub CE CE times the latent force. Now, what we have is 0. This is equal to 0, equal to this one, delta sub CE, and plus this one, F sub CE CE, and then it's time the latent force. Now, we have the latent force equal to delta sub CE divided F sub CE CE. This is going to be the compatibility equation for this truss. And next step, we are going to determine the force displacement relationship. So, third, determine the force displacement relationship along CE line, okay, which is going to be delta sub CE and F sub CE CE, and by using what? The method of virtual work. Use the method of virtual work. And by using the method of virtual work, we're going to determine the deformation along delta sub CE. So what we need to is, we're going to have 1 point unit load. The next name of this method is unit load method, right? So we require a unit load to put into the structure to produce the external virtual work, and it's going to be in the CE direction, right? Because we are going to determine in the CE. So what we have is, we're going to put this one 1.0, and this one is 1.0, and this one will produce the internal force N. What we have is this 1.0 times this displacement 1.0 times the delta sub CE. This is going to be the external virtual work. And then we know from the previous chapter, this is going to equal to internal virtual work. Internal virtual work is this N times the change in the length of each member. So it's going to be N times this is NL divided by AE. Okay, that is the first one to determine this. And we also determine this. That means is the displacement along the CE. So the 1 point unit load also provide along that. Again, we have 1.0. And now it's time F sub CE, F sub CE, CE. This is going to be the external virtual work. And it's going to equal to internal virtual work. This produce the force N. The force N will time the deformation or the displacement of each member. Since this one compute by the F sub CE equal to 1. When the F sub CE equal to 1, the truss here going to be the same as this one. So this one going to be the summation of N square. And then you time L over AE. Okay, that is the two equations that we are going to use to solve this problem. And now we are going to determine the axial force in the truss members. Okay, that is going to be this one N and also this N. Okay, and what happened is the problem gives us the N already here, the capital N. So this is going to be the internal force N, and this is going to be the internal force small n. So now we got to set up the table to compute what we should have here, right? Okay. 1, 2, 3, 4, 5, 6. Let's have 6, total 6. Yes. 1, 2, 3, 4, 5, 6. Well, I'm talking about the 6, and I will show you this is going to be the member. Okay, and then from the equation we have the member A, B, C, D, E, F, and the author. How many members we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, you get this table. We're going to have the table because we're going to do the summation. It's convenient to do this and just text the member AB, 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 BC, BC, CD, CD, and then EF. This all going to have 3, 3, 3, and 3. Okay, you have this one for the L meter, and you may have this one for 3.0, 3.0, 3.0, and 3.0. Okay, next you may set for BE and CF. That is going to be the length is going to be 4.0 and 4.0. And the last one, the last four, AE, BF, CE, and DF. If you do like this, you're going to get the order of this is 3, this is 4, so this is 5, 5, 5, 5, and 5. Okay, and from this equation, you have what? You have the member, you have L. AE, you don't need to because AE, they set up to be a constant of 20,000. All the members have the same AE. And then you have the N, right? So you have the N, the N, kilonewton. And you must copy all the N from here. Like this one, it's going to be plus 3.0. This one plus, you said this is plus, right? It's tension, intention, 2.625. And this one also intention, plus 2.625. And this one is in. Okay, this one is minus 3.0. Okay, and then you copy all of this. This is 4, right? This is gonna be BE 4, and this is gonna be 3. This is tension. This is tension 4 plus 4.0 plus 3.0. This one is in compression, so you put this one is minus 5.0, and this one is in tension plus 0.625. Between this, along the line of CE, there is no, so this one must be 0. And the last one is here, is compression. Okay, you must be very careful on this. Put everything into your table. And then you have the small n now. Small n. We have the n here. Okay, and it's here. This is the n. So 0. This is minus 0.6, 0. And this is what? Minus 0.6. And this one is in compression, right? This one is in compression, so. And you take the order, it's going to be AE 0. BF is this one. This one is tension. Plus 1.0 plus 1.0 CE for sure. 1.0. And this is apply force of 1.0 here. And the last one is going to be 0. Okay, now from this one you have N, small n, capital N, and L. Anyone that you time it and then it has 0, so this is 0, 0, 0, 0, and this one also 0. That help you in the calculation a lot, right? And then you do the calculation of this of minus 4.725, and this is going to be plus 5.4. This is minus 12.8. This is minus 9.6. And this is plus 3.25. And you got the summation of this. Okay, that is the summation of this portion. And this is going to be minus 18.6. Okay, and if you do this, you're going to get delta sub CE. Delta CE. So you got what? 4, 5, delta sub CE, and F sub CE. So delta sub CE going to be equal to this one, minus 18.6 divided by AE. That means it's going to be in opposite to this direction. Okay, if you take this member, this force 1 unit, act in this member as the tension. Okay, if this is negative, so this one going to be equal to 18.6 over AE, but the member now is going to be in the opposite of this, so the force is going to be in compression. Okay, and this one going to be in contraction. It's negative. Okay, another one, you got n square, and now L. Yeah. So for the n square, 0, 0, 0, n square, 0, 4, 0. And this is n square times L. This n square is plus times 3 is plus 1.08. And this is 1.08. And this is plus 2.56 plus 2.56. and this is plus 5.0 plus 5.0, and then you get the summation of this again. You have this for plus 17.28. This is plus, so it's going to in elongation because it's in tension, right? So our F sub CE gonna be 17.28, and then divided by AE, and this is going to be in positive, so this one is going to be elongation. Okay, now after this we may go by putting this force displacement relationship, and then you can find the redundant force. So 1, 2, let's see, 4, 5, the redundant force F sub CE. Okay, and then everybody can do it. F sub CE gonna be, don't forget about this one. Oh sorry, this is wrong. This is supposed to have negative here. So we have negative here divided by, this is negative 18.6 divided by AE, and then this one going to be 17.28 also divided by AE, and you may have this one cut, and this one cut. You may get this one of 1.076. This is 1.076 kilonewton, and it's going to be in this direction. Okay, so now your task gonna be I use a bigger scale, 1.5 centimeter for 3 meter. Okay, your task is going to be like this, and follow what we have before. We have the force in this member of 1.076. This is 1.076 kilonewton, 1.076 kilonewton, and this is subjected to the force of 4.5 kilonewton, and this is 3 kilonewton. And previously you have this reaction as before of what? Of 4 kilonewton, and this is going to be 3.5 kilonewton. And you also has this one for plus 3 minus 5 minus 4.77775 and plus 2.625. Okay, now that is you guys gonna do determine the force in this member, in this member, in this member, okay, and in this member, and then you can answer into this, right? As it's going to be A, B, C, D, E, F. You do by using the same method of section or method of choice. Mostly you're supposed to use method of choice. Okay, after you're doing that, you're going to get this one for 1.979 kilonewton is in tension, and 646 must be 646 kilonewton, and it's going to be in compression. And then this one going to be 3.139 kilonewton, also in tension. This one we also have it for 1.076 kilonewton in tension. And this one is 1.701 kilonewton in tension. And the last one is 2.139 kilonewton in tension. Okay, After you do this, you're going to get all of the required forces in the member, and you may see we have the maximum force of 5 in compression here. Okay, this is less than 5. Okay, that is for the clips of the statically indeterminate truss by using the consistent deformation method. This one's special because it's internally statically indeterminate. So we use the truss member force as the redundant. So we use the CE. Let's we use this. When we use the CE, the structure will change from the indeterminate to the determinate. However, the force F sub CE going to be the redundance. And then you can separate this truss into 2 cases based on the principle of superposition. One subjected to the applied force, another one subjected to the redundant. And if you consider the deformation of this structure, especially along the CE line, you can write the compatibility of 0 equal to delta sub CE plus F sub CE and times the redundant force. So the equation of the redundant force is going to be this one. Don't forget the negative sign over here also. Have this one for the negative side. And then the problem change into the what we have learned before, determine the force displacement relationship by using the method of virtual work or any method that you like. And finally, you get the F sub CE of this. Okay, when you get this, you put into this equation. Sorry, you put this for free body diagram. And then you may cut this one between this force and this force. You may cut this one between this force and this force. And later you can determine this force. Okay, this is the end of the clips. Okay, I hope you guys enjoyed it and try to do it by yourself. Okay.